Okay, Unit 5, Lesson 1, homework video. Implicit derivatives. Derivatives of implicit equations, non-functions. X squared plus y squared equals 5. All right, so to go over the procedure, we start by taking the derivative of everything. With the key thing that we need to remember is that the derivative of y, we say, is dy dx. Okay? But if we have something other than just y squared, we need to use the chain rule. So we have 2y, so that's like the derivative of the outside. I'll just show it for this example, but then in the future we'll kind of understand what's going on. Derivative of the outside is 2 times whatever's in the inside. Derivative of the inside is dy dx, which is why I need not just 2y, but 2y dy dx. Don't forget to take the derivative of the right side, which is 0. We'll then solve for dy dx algebraically. In some cases, we'll have to combine all the dy dx's to factor out, move all the other stuff to the other side, divide. In this case, I just need to subtract 2x and then divide by 2y. I get dy dx is equal to negative 2x over 2y, which is just negative x over y. Okay, but remember, algebra. So let me just show it for this first one. Algebra. Don't just move 2x. You subtract 2x so that this is 0. You have 2y dy dx equals negative 2x. You then divide by 2y to give you negative x over y. All right. We have to be careful with the products and product rules. So x squared times y squared. We're finding the derivative at the point when given. So some of the equations, I just want the tangent slope generator. This is a circle. The tangent slope generator for a circle will always be something like this. This is not a circle. We could start looking at the graphs of these, though, just because it will be interesting. X squared, y squared, we're going to focus on at 3, 1. Here's what the graph of x squared, y squared equals 9 looks like. At 3, 1, it looks like I'm going to have a negative tangent slope, okay? It looks like it's fractional. Let's find it. So, product rule, take the derivative of everything. Don't forget the product rule. Derivative of the first times the second plus the derivative of the second times the first. Don't forget the derivative of the right side. Again, we will move the stuff that does not have a dy dx over. So I'm going to subtract the 2xy squared. Maybe move the dy dx in front of the 2yx squared, and then we divide. We'll be able to cancel the y's, the 2's again. We'll have negative x squared, negative xy squared over yx squared. Then I'll just say at 3, 1, and that'll equal, probably like proper notation would be dy dx at 3, 1, and then I'll just write it down here. We have negative 3 times 1 squared over 1 times 3 squared. So this is negative 3 over 9, which is negative 1/3. So this is negative 1/3. And just like I saw, 3, 1 looks like a negative slope. All right, we got another one. Y cubed plus 4y at 4, 2 equals x squared. Difference between this one and the last one is that we got multiple y's. We got something on the right side we need to take the derivative of. So make sure the derivative of x squared, you know, is just 2x. That's not 0. Derivative of 4y, like 4x. Derivative of 4x is 4. Derivative of 4y would be 4 dy dx. Now this is the situation where we'll start to look at factoring out a dy dx so that I can divide to solve. Now I can divide all of this 3y squared plus 4 because it's multiplied by the dy dx. And I get 2x over 3y squared plus 4. Let's look at the graph at 4, 2. Let's just make sure things will be right. Y cubed plus 4y equals x squared. Cool? Looks like this. At 4, 2, I'm going to have a positive tangent slope. Maybe it's close to 1. Let's see. At 4, 2, I get 8 over 3 times 2 squared, which is 4, plus 4, 12, 13, 14, 15, 16. 8 over 16, so I was wrong. It's closer to 1/2, but whatever. All right, moving towards, I believe this is an ellipse, could be a hyperbola, a rotated hyperbola. Let's see, x squared minus 2xy plus y squared. Oh, this is a pair of parallel lines. This is cool. You'll see this when we take the derivative, but we can actually factor this. There's a reason why there's a pair of parallel lines. It's a cool looking thing, but you'll find out when we take the derivative, we're going to see something very interesting. Don't love this example. Won't happen always. We'll see with the other examples. It's not going to happen, but just make sure we're doing everything properly. We got the derivative of x squared 2x. Now, I'd like to leave out the minus 2 and use the product rule on the x and y. So, the derivative of x times y plus the derivative of y times x. Make sure we distribute the negative 2. You could bake it in, so it's negative 2x times y. I don't know, I go back and forth each year which way I prefer. But as long as we get 2x plus negative 2y plus negative 2yx dy dx plus 2y dy dx, then we're fine. That's not right. This is just 2x. Okay, subtract the 2x, add the 2y. I show all the steps here. In the future, I'll kind of do this all at once. Subtract the 2x, add the 2y. Factor out the dy dx. Divide to solve. What do you see? That's just 1. Y, you can actually factor this. This is x plus y squared, which equals 2. You can kind of square root it, and then you would get, like, why is this a parallel lines? You could actually write this as x plus y squared. It's actually x minus y squared. Equals 2. Square root it, you get x minus y equals plus or minus root 2. This is 2 different lines. You have y equals x minus root 2 and y equals x plus root 2. This is how we see that. Oh, the slope is 1. I wouldn't do this, but I'm just showing you how, like, why is that a pair of parallel lines? It's not that important, to be honest. All right, another derivative, no point, so square root is x to the 1/2. Bring the 1/2 down. X to the negative 1/2. Bring the 1/2 down. Y to the negative 1/2. dy dx. 9 dy dx. I rewrite this as 1 over 2 root x. This is 1 over 2 root y. This is, okay, now it's up to you what you want to do. But you'll find that, I'll show you both ways you can do it. You can either move your dy dx's to the left, which means everything else is going to be moved to the right. So let me show you what that means. I'll have like 1 over 2 root y dy dx minus 9 dy dx. We'd have to subtract 9 dy dx. And then I'd subtract the 1 over 2 root x. Then I'd factor out the dy dx. Then I divide. Now, you're probably thinking to yourself, gosh, this looks messy. And you'd be correct. And could we simplify this a little bit? I'm certain we could. But remembering that we just have a tangent slope generator, and we could use this to generate tangent slopes, this is fine. Leave it like this. Okay, now, you see I got the negative, I got the positive, I got the negative. Let's see what happens if I move my dy dx's to the right. I'd leave the 1 over 2 root x, and I'd have like 9 staying positive, and then I'd subtract the 1 over 2 root y dy dx. I'd factor out the dy dx on the right side. Where it ends up, it doesn't matter. And I divide, getting me dy dx equals 1 over 2 root x over 9 minus 1 over 2 root y. Opposites of each other, but notice, if you factor out a negative from this, you get the same thing as that. So they're equal to each other. Don't freak out if, the answer that I show is opposite the answer you show in terms when we're talking about a fraction. It'll end up being the same when we, either factor out a -1 over a -1 or something like that. Okay? So I won't do that again, just knowing that it doesn't matter which side you go. These are the same. Let's look at this guy. I'll look at the graph of it later. Let's just get through this first. Start with the product rule. Derivative of the first times the second plus derivative of the second times the first. Derivative of 3x. Derivative of y cubed. Derivative of 3, 0. Again, move the dy dx's to any side. You already got the 2xy and the minus 3 over here. Might as well leave it. Move the x squared over. Factor out the dy dx. Divide to solve. We're going to find this at 2, 1. Two times 1 minus 3 over 3 times 1 squared minus 2 squared. So 4 minus 3 is 1. 3 minus 4 is -1, so I get a slope of -1. Let's look. X squared y minus 3x equals y cubed minus 3. Whoa, that's pretty cool. We were looking at the point 2, 1. So 1, 2, 1. I guess it's 1, 2. This is 2, 3, 4, 5. 1, 2, 1. Looks like that slope is -1. Is that even a point? Did I make a mistake? 4 minus 6, -2. 1 minus 3, -2. Yeah, I guess that's right. Tough to tell with the graph. Okay. Trig functions. Derivative of cos y or sine y would be negative sine y dy dx. So make sure we remember the dy dx afterwards. So if I take the derivative, here we go. I'd get 1 plus derivative of 2 sine would be 2 cos times dy dx equals 0. Subtract the 1, divide by the 2 cos y. I won't show all the steps there. At 1, 0, negative 1 over 2 cos 0, cosine, horizontal, horizontal, at 0 is 1. Okay, cool. 2x sine y 4x. It's not just a constant. Okay, this is a good one. I'm glad I have this constant here. I have a constant. Product rule not needed. Because it's just a constant. But if it's x, product rule needed. A lot of students mess up with that, but let's hopefully we've done enough so that we understand not to forget about constants. Derivative 2x2, derivative of the first times the second, plus the derivative of the second, cos y dy dx times the first equals the derivative of 4x. Subtract the 2 sine y, divide by 2x cos y. I could do that all at once, but if you are confused by it, just do it one step at a time. Okay? Yeah, tangent. Do you remember the derivative of tangent? Secant squared. It's just a constant, no product rule needed. I would need a dy dx after this. Subtract the 3 secant squared x, divide by 2 secant squared y. And it's just fun to look at some crazy graphs like that. It might not be that crazy. Sometimes I think some graphs are going to be really crazy. They end up not being that crazy. Let's see. It might be small because, like, oh no. It might not even graph for us. It might just give up. Oh, well, yep, I was right. It's crazy. That's so cool. So because, like, tangent's undefined at so many locations, there's all these locations, these lines, where you don't have any graph, including y values, tangent of pi over 2, so negative pi over 2. Oh, it's pretty sweet. X values as well, where we're undefined, but then we have all these like little pieces of graph in there. Cool. All right, tan inverse y. All right, and I got a point to plug in. Let's see how that works out. Okay, tan inverse. We remember the derivative from last unit. 1 over 1 plus quantity squared times the derivative of the quantity. This would be y squared times dy dx equals derivative of x is 1. I'm going to multiply by 1 plus y squared. It ends up just being 1 plus y squared. So at pi over 4, 1 plus pi over 4 squared, which is 1 plus pi squared over 8. This is 8 over 8. If you want to write it as 8 plus pi squared over 8, you could do that. I think what I wanted to do is just talk about, like, what is the tan inverse of pi over 4? You should be able to know how to do this. It's the same as asking, let's just say this is an x. If you took the tangent of both sides, that pi over 4 is equal to the tangent of x. That's not right. Never mind. I'm thinking of something else. Arctangent of 1. I should have had these points flip-flopped. Arctangent of 1 you should be able to do. tangent of both sides, you'll get pi over 4. Okay, so I'll try to put that in more. All right, to some tricky ones. Sine of x, y. I'm going to do a different one for the next one because I want us to understand. Let's do another one like sine of x plus y equals y. I just want you to see the difference between the derivatives of the two. I'm going to actually start with this one here. Okay, now O's and I's are important to understand here. The outside is the sine. The inside ends up being the x plus y. We didn't really have to worry about this for any of the ones on the previous page. Derivative is cosine. The derivative of x plus y is 1 plus dy dx. Watch how this derivative looks. Cos x plus y times 1 plus dy dx. That equals dy dx. Now here's the problem. I can't just divide by the cosine xy because then this dy dx is going to be trapped. I can't subtract the 1. I can't divide by the dy dx, 1 plus dy dx, because then this 1 is going to be trapped in the parentheses. The best thing to do is to distribute. Distribute cos x plus y to both of those. Watch what happens. The parentheses and the multiplication go away, and we will be able to manipulate what's left over. Now, move things to one side. It doesn't matter which side you moved it to, just like don't be afraid if your answer is opposite of my answer. I'm going to move it to the right side so I don't have to move two things. I don't know why I moved it over there, but whatever. I get cos x plus y equals dy dx 1 minus cos x plus y. Divide dy dx equals cos x plus y over 1 minus cos x plus y. Okay? Now, here, watch how it's going to be a little bit different. Sine, the inside is xy. The derivative of sine, cosine, the derivative of xy, you need to use the product rule. Derivative of x times y plus the derivative of y times x. So, I'd have cos xy times y plus dy dx x equals dy dx. Just like the previous one. To be able to manipulate things when we have dy dx's on both sides, but we have parentheses and multiplication, we need to distribute. Distribute the cos xy to the y and to the dy dx. You get y cos xy plus dy dx x cos xy equals dy dx. Again, move things and divide. Maybe I'll subtract. The dy dx x cos xy. Factor out. Divide. Okay. Tangent. Sure. Same thing. I'll do this one quickly. It'll be 2 secant squared xy times 1 plus, derivative the first times the second, so it would be y plus dy dx x equals 1. I can not distribute. This is a good example because this is a 1 on the right side. I could just divide by the secant squared times 2. And then subtract the y and then divide by the x. Now, will this look pretty? No, but you can do this. Still tangent slope generator. It'll be a little bit messier than if you distribute. I'll just show if you distribute. You'd have, I'll just do it quickly, 1 minus 2 secant squared xy times y, so I guess 2y secant squared xy over x, 2x secant squared xy. Okay, but they're the same. All right, now we got e's. We'll have logs. Find the derivative. Derivative of the e to the x, that's great. Derivative of the e to the y. Using the chain rule, it'll be e to the y times dy dx. Derivative of 2x is 2. Subtract the e to the x, divide by e to the y. You want to find it at the point 0, 0? Sure. 2 minus 1 over 1, slope is 1. E to the x plus e to the y equals 2x. Let's see what that looks like. E to the x plus e to the y equals 2x. Wolfram does not like this. Okay, never mind. We will never know. Sine x e to the y minus e to the y cubed. Go to sinus cosine. E to the y would be e to the y times dy dx. Derivative of e to the y cubed. So just to confirm things, the outside is e to the power, the inside is the y cubed. So watch. The derivative of the outside, e to the power, derivative of the inside, 3y squared dy dx. So it'd be e to the y cubed times 3y squared dy dx. Factor out the dy dx. Divide to solve. Okay, we got a product rule in the power. Let's see what we got. E to the xy. Outside, inside. The outside e to the power, the inside xy. When you take the derivative of xy, you need to use the product rule. That is the important part. Derivative of the outside, that's easy when it's e to the power. So I'd get e to the xy times y plus dy dx x plus 2y, just 2y dy dx equals the derivative of e. This is just a number. Doesn't have e to the x. It's just a number. 0. Derivative form, just 0. Now I want to be able to factor out the dy dx, but again, I can't because of these parentheses. Like this dy dx is trapped inside, so I need to do distribute. Giving me y e to the xy plus x e to the xy dy dx plus 2y dy dx equals 0. Subtract the y e to the xy, factor out the dy dx. I'll show you both of those steps at once. Okay, so I subtracted this over, it comes here, factored out the dy dx from this, I have x e to the xy plus 2y, and then divide to solve. Okay. At 1/2, 2. Great. I get negative 2e to the 1/2 times 2 is 1 over 1/2 e to the first plus 4. Could I simplify this? I'm sure I could, but that's it. Do I need to simplify this? I don't know. Let's just prepare ourselves to simplify this. You can multiply the top and bottom by 2. You get negative 2e over e plus 8. That's to the extent of what I would do. Is just get rid of this fraction in the denominator. You can't simplify the e's because of the plus, so you would stop there. I forgot to multiply the top by 2. Okay, now this, very interesting, have to use the product rule. All right, so we got to use the product rule. Derivative of dy dx, of y, dy dx, derivative of first times the second, plus derivative of the second, e to the negative y times negative 1 dy dx. So the derivative of negative y would be negative dy dx. That's equal to 1. I can factor out the dy dx. I get e to the negative y minus e to the negative y. What? Oh, this might be interesting. This is just 0. I think the slope of this is just 1. But that can't be. Maybe I made a mistake. Let's look. Y e to the negative y equals x. Whoa. Slope's not just 1 everywhere. Where did I make a mistake? To the first times second plus. Oh, Mr. Messner. Classic error. Derivative of the first times the second plus the derivative of the second times the first. I need a y here. I need a y here. It's silly. 1 over e to the negative y minus y e to the negative y. This is very like a great example of like you really have to be careful. Notice all the work that I'm doing for all of these. I'm like very proficient at this, and I could go a little bit faster, but not too much faster. You really have to show all of your work to do these correctly. All right, let's see. We got logs now. Let's just talk about really quickly the derivative of log y. Derivative of log is 1 over. So I'd have 1 over y dy dx. Some of these derivatives are actually nice and easy to simplify. Derivative of 3 log y would be 3 over y times dy dx. This would equal dy dx. Again, it just so happens that it might be easier to move things to the right side. Factor out. Divide to solve. At 1, 1. Cool. 2 over 1 plus 3, 1/2. log x minus 3 log y. I know I'm going to be contained to the first quadrant because I can't plug in any zeros or negatives into logs. So I'm looking in the first quadrant. I got an integer solution, which is what we looked at the tangent slope for. And it has given up. It's like, no, I don't even want to do what I just did. All right, well, that's the slope. All right, let's look at this guy. I got dy dx equals 1 over xy times the derivative of xy, derivative of the first times the second, plus the derivative of the second times the first. You need to be able to do this without just looking. Now, okay, the next one will cover this. Again, dy dx on one side, dy dx trapped in parentheses on the other side. You got to distribute. That way you can easily manipulate. You won't always have to. If you don't have a dy dx on the left side, then you'd be fine. You got y over xy, y's cancel, that's nice, plus dy dx x over xy. Since it's multiplication, the x's cancel, that's nice. So I got now dy dx 1 over x plus dy dx 1 over y. I can, I don't know, move the dy dx, subtract it. So I got dy dx minus 1 over y dy dx equals 1 over x. Factor out the dy dx, 1 minus 1 over y equals 1 over x, divide. I'm okay with this. Sometimes you'll see things that are not as simplified. You can multiply the top and bottom by x and the top and bottom by y. And instead of having all these fractions inside of fractions, you'd have y over x y minus x. So top and bottom by y, y minus 1, and then I'd have y over x, top and bottom by x, just leave y. So like be prepared to simplify things like this so that you don't have fractions in the numerator and the denominator. Other ways to do that as well. All right, equation of tangent lines. Sweet. All right, well, I need a point and a slope. I got a point, so I need the slope. I need dy dx. Let's take the derivative. Now, it's the same process as we've been doing. We've been finding derivatives. Maybe let's talk quickly about log of x squared plus y squared. The derivative of the outside would be 1 over. Derivative of the inside would be 2x plus 2y dy dx, which is why I got this as my derivative. Now watch. I don't have to distribute because this is just a 1. I just have dy dx here. I could just multiply by x squared plus y squared. I don't want to say don't distribute. You could. It'd be messy, but it'd be fine. I'm going to say don't have to distribute. Multiply by x squared plus y squared. You get x squared plus y squared equals 2x plus 2y dy dx. Subtract the 2x, so I get x squared plus y squared minus 2x divided by 2y. At 0, 1, 0 plus 1 minus 0 over 2. It's just a coincidence that all these slopes have been like 1s and 1/2, so it won't always be like that. Yep. So Equation of tangent line, y minus 1 equals 1/2 x minus 0. So y equals 1/2 x plus 1. Why don't we see if we can see our handiwork here. Oh, there we go. Cool. 1/2 x plus 1. Come on. Oh, wait, it had it. Doesn't have it. Oh, yep. Yes! Sweet. There it is right there. And 0, 1, that was like right in this spot right here of this little graph. Okay, now we're going to do a tangent line approximation. Find the tangent line approximation for k if 0.1 k is on the graph of the previous equation. Well, I'm going to use y minus 1 equals 1/2 x minus 0 to approximate x equals log x squared plus y squared around 0.01. Well, 0.1 is close to 0, so this will work. 0.1 is an x, so I plug in 0.1 for x. So 1/2 times 0.1, so that's 0.5 times 0.1. Prefer to use decimals because 0.1 is easy. You just move the decimal place over. So y minus 1 equals 0.05. I think y equals 1.05. We could actually solve this if I plugged in 0.1 into x. .046. It's close to 1.05, which is what I just found. That's great. And we did it. So y is k. K is approximately 1.05. Do the same thing for, gosh, let's change this. I know this is going to be messy. This slope is just 1. I'm going to change it. So I apologize. Change this to a 4. Wait, no. Yeah. Change it to a 4. You don't want to use the 2 because it ends up a pair of parallel lines. Now this is not a perfect square. So now this is fine. Sorry about that. But now the point doesn't work. Okay, we're good. Let's just keep going. If x is 2, 4 minus 4 times 2. Let's use 3. 4 minus 24 plus 9. Negative 20 plus 9. Negative 11. Change this to negative 11. Just double check. 4 minus 8 times 3 plus 9. Good. Okay. So change the equation, please. All right, let's go. Derivative of 2x. You can either bake in the 4 or leave out the 4. I don't care. Let's bake it in. Derivative of negative 4x times y plus the derivative of y times negative 4x. The negative 4 gets baked in. 2y dy dx equals 0. Subtract the 2x, add the 4y. Factor out the dy dx. I'll show all the steps. This is one of those derivatives that has nice symmetry because it's either like a hyperbola or an ellipse. And we're going to focus on 2, 3. So at 2, 3, I get negative 4 plus 12 over negative 8 plus x. So I get 8 over negative 2, which is negative 4. So y minus 3 equals negative 4 times x minus 2. I already have the point, I just needed the slope. All right, find the tangent line approximation for k, comma 2.75, if that's on the graph of the previous equation. So I'm going to use y minus 3 equals negative 4 x minus 2 to approximate x squared minus 4xy plus y squared equals negative 11 around 2, 3. 2.75 is close to the y coordinate of 3. Now understand that this is a y coordinate, so plug in 2.75 for that y coordinate and I will be solving for x. Or really, you could plug in k. I didn't do this in the previous one, but you could have. This is negative 0.25, so negative 1/4. Negative 4k plus 8. Subtract 8, so that's subtracting 32/4. That's negative 33/4. I will divide by 4. K will be approximately positive 33/16. Let's do it really quickly. First, let's graph x squared minus 4xy plus y squared equals negative 11. I think it's a hyperbola, not an ellipse. Yeah, it's a hyperbola. So symmetry with the slopes. And if I have a y coordinate of 2.75, I'm just going to have 1x. I could do this by hand, but this is just a little bit easier. I get 2.0813 or 8.9187. I'm looking for the one close to 2, 3. 33/16 is 2.0625. So this is 2.0625, and I got, for an actual, 2.08. Okay, pretty accurate. Definitely accurate to the first decimal place. All right, so what have we learned today? We learned to pay attention to details, show all your work, practice. We really need to practice all of these derivatives because they are tricky, and they are long, and they involve attention and details. You know, I've had problems in the past with my x's and y's looking similar to each other. So make sure your x's and your y's are nice and neat so that you don't confuse one for the other, okay? Be nice and neat, show all of your work. Good luck.